Okay, hello. Good evening, everybody. My name's John Parker. I'm Technical Director here at the Arboricultural Association based in Stonehouse in the UK. And thank you all so much for joining us for this special virtual Arb Show webinar entitled An Introduction to Wood Inspection. This is the first of 3 sessions happening at 6 o'clock each day. Today, tomorrow, Sunday. Today, we're joined by Mark Vestey from our main event sponsors, Sorbus International, for an insight in some of the latest decay detection technology. Huge thanks to Mark and the team at Sorbus for providing this session and for their amazing support of this event as our main sponsor. It's now been over 2 years since the last Arb Show. It's been a very long time since we've been able to catch up face to face as an industry, connecting with old friends and new at events that the Arb community usually looks forward to as part of its calendar. It's been a very strange time indeed. I know that the team at the Arb Association have certainly missed these opportunities. I'm sure many of you watching have as well, but things are starting to look up. And on Thursday, we opened booking for our first major in-person event since September 2019. The Arb Association conference this year is on the theme of trees and society. It's the 54th Arboricultural Association Amenity Conference. We can't wait, is what I meant to say. We can't wait to welcome delegates to a new venue at Loughborough University, where you'll be able to enjoy some remarkable speakers and exciting new features. We hope it'll be the perfect chance for the arboricultural community to catch up. Back to this evening's virtual Arb Show session. Thanks to all of our exhibitors who populated the virtual showground. There's a great range and they filled the show with lots of video content, special show offers, and plenty of ways for you to get in touch with them. Please take the time to visit them all, explore all of the features of the virtual Arb Show. I should mention here, thanks very much to Steve, to Jason, to all the team at the association for all the work that's gone in to putting this fantastic event together. There's loads of interactive content, but most importantly, of course, you've got the chance to win the opportunity to name the 2022 Arb Show beer. Yes, that's right, folks. The 2022 Arb Show beer. You can name it and you can win some great prizes as well. We're going to be posting links to relevant things in the chat, including registration links for our Saturday and Sunday webinars. If you'd like to ask Mark a question for the Q&A session, please post it using the Q&A function on the webinar. Don't post it in the chat. I'll miss the question if it goes in the chat. I'll have to keep track of it on the Q&A panel. Don't forget to say hello in the chat. Let everyone know where you're watching from. We've got some great places. I'm looking at a few things here. Everyone's watching. It's all very exciting, but all panelists and attendees is what you need to do. So that's my bit done. That's the boring bit. I'll now hand over to your speaker for this webinar, Mark Vestey, who's the Technical Support Manager at Sorbus. Mark, over to you.
Thanks, John. Good evening, everybody. Hope you're having a nice evening so far. Okay, so we're just going to go through a presentation, which is an introduction into the Pickers 3 sonic tomography system and the IML Microdrill. Okay, so we're going to go through the resi PD mainly. Tree inspection methods. There are many tree inspection methods. Probably the most important one that we tend to start with would be something like the VTA. So this is where your visual tree assessment comes in. This is your knowledge, your experience, your mallet, probe, tape measure, clinometer, all the bits and pieces. From there, we can then maybe, if need be, go on to the more technical inspection methods. So we have the SOT, sonic tomography system. We have the ERT, electrical resistance tomography. We have the pull test system. We have the tree motion sensors, and we have the IML resi microdrill. Now, with all these pieces of equipment, the aim of the game is to find out the truth behind the defect that we're looking into within the tree. There is an element of estimated guesswork, if you like, to try and come to the closest conclusion possible. And using all the bits of equipment and your knowledge and experience, we aim to get to the correct decision. So the IML Resi PD, it is used for anywhere where there's wood and there's public, then there is a possible risk, and that risk needs to be assessed. With the assessment of that risk, we use the Resi PD. The Resi PD, in this case, we're going to be looking at tree inspection, but it is used in all aspects of life where there is wood. So utility poles, playground equipment, historic buildings, bridges, anywhere on the railways with the timbers, and utility poles is one of the biggest users, I would say, for the IML Resi Microdrill. What is a microdrill? This is a microdrill. This is a 3mm cutting head on the end of this needle here. It has a 1.5mm needle shaft, hardened steel shaft. And we're spinning this needle as a standard RPM, we'll be spinning this at 2,500 RPM. And we're measuring the resistance on the tip of the needle as it's cutting through the fibers of the wood, and also as it's pushing itself into the wood. So we're measuring two things, the feed and the drill. So wood damage is kept to a minimum. You can see it's not a fluted needle. It's not pulling out the wood chips. It's destroying the fibers, and the chips are falling behind the needle head. And then when the needle reverses out of the channel, it actually leaves the fibers in there. So it doesn't actually create a hole as such, but it does create a slight bit of damage, a minimal bit of damage. This is a drawing from Matek. You probably recognize the drawing. And on the right-hand side there, we have the motor doing the turning. And on the left-hand side there, we have the wooden fibers as the needle's penetrating into those. And then we also have the frictional drag that can be on the needle. So the deeper the needle gets into the wood, the more the tree wants to hold the needle shaft and increase resistance as it's spinning through the wooden fibers. So we have to be aware that we look out for frictional drag. Okay, so we have the motors with frictional drag, and we have the wooden fibers. So the reason the PD is so popular is because the PD has two motors to do the turning, which we'll go into in a second. And the feed motor actually goes into and past the frictional drag, so you don't have the resistance on the turning motion of the drill. So we can feed the drilling needle into the wood at up to 200 centimeters a minute. There is 5 standard gears, if you like, a bit like gears in your car, 1, 2, 3, 4, and 5. Number 1 is slow, high torque, and that will penetrate into the really hard woods, the tropical woods, and your home oaks and that kind of stuff. And then you have speed 2 and speed 3, so that would be your beech and your oak. Speed 4 and speed 5 would be things like your lime and your poplar trees that are very soft and easy to penetrate. So the reason we change the speeds is that we keep the amplitude of scale, and I'll go into this in a second, on the drill graphs. Okay, we keep the amplitude somewhere where it's legible, and we can see drops in the resistance in the amplitude on the graph if we hit decay and a pocket or crack or cavity or even incipient decay. And we see peaks in resistance as we hit harder objects such as knots, reaction wood, and coatable. So we have an OLED display you can see on the top right-hand corner there. That gives us all the information we need while we're on site. That will give us our speed, that will give us our ID so that we can identify the drilling that we're actually doing. It will show us our graph, both of our graphs. There is also an optional Bluetooth printer, should you wish to print out a one-to-one piece of paper while you're on site. If not, it saves all the drillings into the memory, and then we just transmit the drillings back to your PC. Or if you have the new freely available app, IML Studio, which you can download from the App Store, then you can download it while you're on site and send it off to the office or store it, or you can do both. You can download it to the app, and you can print it, and you can send it to PD Tools Pro, which is the software that comes with the system itself. So if you are to buy one, this is what you get. This is a Resi PD. This is your device in the bottom here. Okay, this is the fast charger. It takes about 30 minutes to charge a battery. There are 2 5-amp batteries. Each battery will give you more than enough usually for a day's work. If not, you get 2 just in case. There's an optional shoulder strap. There's an optional Bluetooth printer. This is your calibration certificate. And then you have 10 spare needles that come with the device in this needle quiver. And there's some various tools for maintenance, changing the drilling needle, etc. This is the Resi PD in action. So I'll show you a quick video, and then you'll get to sort of understand what I'm talking about if you haven't seen a PD before. Okay, so you can see from that video, arriving onto site, the device was taken out of the box itself, and then the tree was drilled in the places where it was deemed necessary to check for problem stability or safety. Then it was taken back to the office after the data was checked on site, and the results were downloaded to the computer, the laptop, and from there you can do an assessment. So that assessment will tell you you've got your bark, you've got your soundwood, you've got crack, cavity, decay, and so on and so forth, so that you can explain it to your customer. And then you can save it as a JPEG, you can paste that into a Word document, you can save it as a PDF and attach it to tree management software. But while you're on site, you see the green display now on here. We have 0 centimeters, so this is centimeters of penetration. At 10 centimeters, it's dropped into the cavity. Okay, and then from 10 centimeters all the way up to the end of the drilling, actually, it was a cavity. But you can see slightly in the solid green color there, that is the drill graph. So that's the rotation. Okay, there's a slight bit of penetration resistance that I spoke about, shaft friction that I spoke about earlier. So from 10 centimeters and further in, there is the shaft friction. The feed graph is the more sensitive one, up to 30 times more sensitive, is the hollow line on the display that you can see there. So the feed graph that doesn't suffer from the frictional drag has dropped off at 10 centimeters and it's actually hit the floor. The reason that's important, in incipient decay or reaction wood, where you're looking for very subtle changes in the wood, that will be picked up far quicker with the feed, such as Crutchmaria. You'll see it actually drop off. Drilling resistance, this is an example. There are 2 graphs. Okay, so this is after it's been downloaded to the software. The blue graph is the feed graph and the green graph is the drill graph. So you can see from 0 to 3 centimeters from down here is your bark, and then from 3 centimeters to 11 centimeters is your soundwood. And then we have the decayed area, and then from 30 centimeters to the end of the drilling, we have a back through the other side of the cavity into the solid wood. The peaks and troughs, they're usually your annular growth rings. As you're cutting through the early wood, late wood, as the tree was growing, the peaks and troughs are showing there like that. So we're looking for a drop in resistance and a smoothing as well of the graph. The smoothing would indicate decay. Another example, so you can see this tree was eventually felled, and we have the bark, we have the solid wood, good compartmentalization, dropped down, a solid stop, the tree has shut the decay off here, and then it's gone off into the cavity itself. I don't personally know this tree. I don't know why it was felled eventually. Maybe it was in a high target area, or maybe it was maybe worse lower down. Can't get much lower. So this is an example of cracks. So you can see 2 cracks here, and you can see the pith. The difference between the cracks is that the feed drops off to the bottom, and the pith is a very quick drop. This is it was an instructor when we went to, Phil and myself went to Merriswood to do college demonstration for students. And they wanted to do an aerial inspection on a tear out that they had on this particular tree. So he was up there, shimmied up there, and he was going around on his rope and harness and drilling in several areas to find out the extent of the wound wood and the damage and if it's coping okay. Slightly older picture now. This is Matek drilling into with Sebastian Hunger, actually on the left-hand side here, holding the drill. They're drilling into a tree. It was in a wooded area in Germany that Phil and myself went on, quite a few years ago now. But you can see the reason why he's drilling it. And we have Mr. Haraway himself. He's drilling into that tree with the first PD, I believe, in the UK. That was Mr. Haraway, Mr. Pickus, Mr. PD. I know he's watching somewhere in the background. First man of the Pickus, first man of the PD, and so on and so forth. This is playground equipment. So obviously it's very important. Children are playing on the equipment, and they are usually covered over like this is here, and you can't see the extent of any damage that may be below. So here you can see this is a pole that was removed. This is below ground level, and this is ground level. So when you're tapping around and you're poking this bit with a screwdriver, the inspector thinks, oh yeah, that bit's okay. And very likely, very possibly it could be decayed, needing replacement. This is HMS Victory. Anyone that's seen any of our presentations before would have seen this photo. This is down in the bows of the down in the bottom of the ship where it's where the public don't go. And some of the most original wood is actually this bit of the keel. Then we have historic buildings. So this is a big old solid oak beam, a bit like drilling into concrete. It's 1,000-year-old. Timber bridges. Okay, so we drilling the bridges, utility poles, anywhere, like I said earlier, anywhere where there's wood. Centre parks use it for drilling, well, not centre parks themselves, but consultants go into there and check the laminated beams that are in the dome. And the underwater device, so this will drill underwater up to 10 meters below ground. No, that's not me demonstrating it. It's way too cold in there for me. But basically it blows air in from the surface. The man on the surface is operating the drill through obviously talking to the guy underwater. Says stop, start, go, and off it goes. Just a short case study. This is a oak with a lightning strike. So the pickers was put on here, the resi PD was drilled, and the comparison was, this is the tomogram, and I'll go into the tomograms with you just after this presentation for the resi PD, and this is the drill graph from that tree. So you can see here the reaction wood. It's very good reaction wood, and then it's gone into the cavity. That's what we're looking for. We want good reaction wood. Okay, so that's the resi PD. Hope you understood that okay. If not, feel free to send me any messages or email me later on. So this is the resi. This is not the resi, this is the Picus. Okay, we're going to be using this for sonic tomography. Sonic tomography history started in the late 90s, and then in 1999 they came up with a device that they could realistically fit to the tree. If anybody was on the webinar with Stefan Rust on Wednesday, he went into a bit more detail about the history early on in his presentation. It's very interesting. And then in 1999, this is how they started. They came up with the tomogram on the right hand side with Lothar Gok and thought, hang on a minute, there's good mileage in here, we could build something. So they built the Picus 1 in 2000 and started to release it. It had a manual hammer, and we used to tap the nails with a manual hammer with a little Y cable on. And then in 2006 they came up with the electronic hammer. This allowed us to have more measuring points and more nails in the tree than there was sensors. With the Picus 1, if you had 10 sensors, you could only have 10 measuring points. With the Picus 2, you could basically have up to about 99 measuring points. And if you have 10 sensors, you'd go around many times. So you put the sensors around, tap all 99, move the sensors, tap all 99, move the sensors, and so on and so forth. The Picus 3 is what we're using today. Okay, so this all comes in a nice little handy carry case. The calipers are in there, the electronic hammer's in there, the Picus unit itself is in there, and then it gets strapped to the tree like this. Still using nails. So how do we get the sonic, the stress wave, the sonic pulse, if you like, into the tree? We're using the hammer, is we use nails. So the nails go through the bark into the wood of the tree, and then that way we can induce a stress wave and listen the other side with the sensors at what time that stress wave gets there, which we will go into shortly. This is the Picus 3, the main unit. These are the sensors around the base of the tree here. On the nails, they're magnetic, so they're just galvanized roofing nails. Then we have the electronic hammer. This is the Picus radio hammer with display, and that is what we're tapping here, this little tapping pin, which goes back into here. So as soon as this part of the hammer makes contact with this part of the hammer, it starts a timer. Okay, that timer is then stopped when it gets to the sensors, and the sensors hear that shock wave come through, that stress wave come through the tree. We also need to know distance, which we measure with the Picus caliper. So we have a start, we have a stop, and we have distance, and we can calculate velocity. How do we decide on the measuring level is quite important. If you have the measuring level in the wrong place, you'll miss what you're looking for. Okay, so when you're doing a Picus tomogram, it's like a sheet of paper through the tree. You're just doing a 2D scan, and you keep the nails as level as you can with the stem of the tree, and you have it in the correct level So if you're looking for decay coming in from the root system, then you need to be as low as practically possible to the base of the tree. If you have a very heavily buttressed tree, then you may need to come up slightly, because it would be nigh on impossible to get really, really low down to the ground when you've got buttresses stretching out several feet. Okay, so we locate the defects with your VTA. So you use your mallet. Okay, you've got your mallet, and then you've got your probe. So we're going to stick this in, we're going to have a look, and we're going to go have a look and find out exactly where we want this tomogram to be. The Pickus assessment, like I said, is a 2D level. We can do several levels. Okay, so we can do one level at, say, 5 centimeters from ground level, and then should we need to, we can do one at 10, 20, 30, 40, 50, as many levels as you like. Each one is an individual tomogram. And then from that, with the expert software, we can produce a 3D tomogram, which I will show you later. This is what happens if you measure at the wrong level. Okay, if you're at 1 meter and you've got root-borne decay coming in, then you're going to miss it. And if you're at the right level, you should be getting the right results. So after we've selected the right measuring level, we correctly position the measuring points. So this is where the nails, it's important to select the correct measuring points. And the measuring points go in where we can map the geometry of the tree. Now, by mapping it, what I mean is if the tree has buttresses sticking out like this, we have a nail on the inside of the buttress, one on the outside, one on the inside, one on the outside, and we try to follow the shape of the tree to create the correct geometry. The more measuring points generally give you a better definition to the geometry and to the final tomogram, because we're inducing more data. It doesn't take too much longer just to use a few more measuring points if you need be. Measuring precise geometry with a Bluetooth caliper is essential. There's no reason in the world why anybody should not be using the caliper, the Pickus caliper, and there are no round trees. So we don't use the original Pickus, didn't have calipers back in 1999, 2000. And the tomogram can be quite severely affected if your geometry is incorrect. Okay, so we install the equipment. We collect the sonic data with the electronic hammer. So the electronic hammer, I can't, it's just there, just in front of the PD. I'm not sure if you can see that. I'll show you that in a bit. And then we go around and we tap all the measuring points. So in fact, I will grab it. And there is a video in a bit, so I'll show you the video. But essentially, this is Pickus radio hammer with display. Okay, we have a little display on the front there, and this just goes around. This goes onto the nails, and then we tap like, well, one at a time. 1, 2, 3, and we do 5 taps on each nail, each measuring point. The computer works out the mean average of the 5 taps and saves that for the final calculation. Check your data while you're on site. Once you've gone around and you've done all your tapping, always check your data. So go through each individual tap and make sure all your taps are correct, because rubbish in, rubbish out. Okay, good data in, you can be sure that you get a correct tomogram. But always, 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 if you get a really bad tomogram, then verify it. And you can verify it with a resi PD microdrill. You can drill in several areas and find out your wall thicknesses. You can use a drill. You can use a Haglöf borer, anything like that. Just verify it before you reach for that chainsaw, because once you get that tree on the ground, if you've done it wrong, it could be embarrassing. And it has happened. People have done it accidentally. Then you get back to the office, okay, and you can do a report. You create your report. You can save it again as a JPEG and just paste it into your Word document, or save it as a separate file. So what is needed? The Pickus itself, this is a standalone unit. You can also use it with the laptop. In standalone mode, you can only have 24 measuring points on the tree. With the laptop, you can have up to 99 measuring points, regardless of how many sensors you've got. You need to know correctly the distances between the measuring points, so we use the caliper. And you need to know the velocity, okay? And that can be worked out with the computer program. As previously mentioned, this is why it's important to select the correct measuring points. If we didn't have nails here, measuring points here, then we wouldn't calculate the main strength part of the tree, as you can see. Okay, so we need to be sure that we're correctly mapped. This is the caliper. This is the caliper. This is a Picus 3 caliper. And essentially, we have a couple of arms that go across onto the nails. We have a display down on the bottom here. We have two little windows in the top here. These two little windows are going to tell me where to put the arms and where to measure. Okay, so when we get to that point, but before we get to that point, we've told the Picus that we've got 18 measuring points. We've told it what species we're on. We're told it how high the tree is and a few other sort of basics. And then it will tell us on here to measure. And what we're doing is what you can see on the screen. So here, this is a smaller tree, shall we say, and we're just using one baseline. One baseline uses 2 base points. So in this particular example, it's base point 1 and base point 6. We triangulate with the caliper twice around each baseline. So this one here, we've come around one side, we come back around the other side from a different point. So the left arm goes around 5, 4, 3, 2, 1. The right arm goes 2, 3, 4, 5. And then we do the same again from the other side. Okay, we do 6, 5, 4, 3, 2, 1, and then back again. And that triangulates and gives us millimeter perfect base point locations and measuring point locations. Now, if the tree's big or awkwardly shaped, heavily buttressed, we may not be able to reach measuring points 1 and 6 with our calipers. Our calipers have a maximum span of 1.5 meters in standard mode. If we put the extensions in the calipers, they have a maximum span of 2.2 meters. Now, if we can't reach 1 and 6, we then need to choose 3 baselines, which you can see on the bottom example. So we then need to be able to reach with the calipers, in this example, 1 and 7, 7 and 11, and 7 back to 1. If we struggle to reach that, maybe 7's around the other side of a buttress, we can move 7 to 6. We can move 11 to 10 or to 12, wherever we can reach nicely. And then we triangulate around the 3 baselines, twice around each one. That then allows us to create perfect geometry. On the top right, you can see a very awkward shaped tree. The left-hand side there is the older style Picus with the older style caliper, but we're still getting very accurate geometry. On the bottom, you can see incorrect geometry can affect the tomogram. So a round tree, not using calipers, still tapping, is it 12 measuring points? You can see the actual tomogram is not right. And then the one in the middle is correct. This is the Picus 3 caliper. Okay, it folds down nice and neatly. You can put it into a little rucksack. You can take it onto the tube, as Mr. Haraway likes to do. All parts of the Picus can be broken down nice and easily. It does come with a little sight bag, so you can see the bag on the right-hand side there, and all the Picus bits and pieces can go into that bag. This is again Mr. Haraway. He likes his big trees. He always tends to get the most awkward ones. Top left, he's got a 3.6 meters on the x-axis and 1.8 on the y-axis. So it's a big old beast, that thing. And then on the right-hand side there, we have the Picus 3, again doing a very awkward shaped tree, which is exactly why we need correct measuring positions. This is 30 measuring points on that one, so yeah, it's a fair old size. Okay, again, this is a tree. This is the Picus 3, and this is the radio hammer with display. Tap in measuring point number 4. This is our tree. There is a defect in the middle. We take our radio hammer after we put our nails into the tree, and we tap each nail. So this example, we're tapping number 1. Stress wave goes through the tree. If there's nothing wrong with the tree, the stress wave will go straight through and it will get to the other side of the tree very fast. If there's a defect in the tree, it will need to go around the defect as it can't go through it. So it will take longer to get there. Once we've tapped number 1, we do the same for number 2, do the same for 3, 4, 5, 6, and we tap all the nails. And then the computer can work out what is going on. Okay, so in this instance, you can see here, there's a hole. And this is how we calculate what's going on. Now that can be affected by decay, it can be affected by cracks, it can be affected by inclusions. multi-stem trees. Okay, so we have to be sure that what we get is actually what is happening. So if you get a bad tomogram, verify that you've done it right and it's showing you the correct result. This is the Picker's reaction. Okay, so it's once you've had the training, once you've had the operator training, it's relatively easy to set up and use compared to the older models, especially. The speed is quite quick. You can get a good result from what I would call a standard tree in 10 to 15 minutes. And on the more awkward ones, it will take you a few minutes longer. What we're actually calculating after we've done all that is the apparent and relative velocities. Okay, they are shown in the tomogram as three main colors. So the brown wood indicates fast velocities. So fast velocities should be good wood. Then we have reduced velocities, so that could possibly be earlier decay. And we have relatively low velocities, and that could infer decay, crack, cavity inclusion, something stopping the stress wave from getting through to the other side. Average velocity at each intersection of the stress wave equals a color. So by each intersection, every time you tap number 1, it sends out the stress wave and all the sensors listen to it. You tap number 2 and all the sensors listen to it, tap number 3, and you're creating a basket weave of lines inside the tree, speed lines. And at each intersection of these lines, we can work out a color depending on the brown would be 100% velocity. So the fastest velocity that the pickers can find on the tree. So it self-calibrates to the tree that you're testing. And then from that, the blue is usually about 50% the velocity of the brown. Okay, the distance between the colors is also important. So we look at the distance and we can see if there's a very short distance between the low velocities and the fast velocities, as you can see just by number 1 in this example here. You can see there's not much color difference between the blue and the brown. And that's a good indication that the tree has shut off the decay and it's compartmentalized. We can see it's slightly spread in here with the lighter colors, and the lighter colors could indicate that the decay is still active and it's still spreading. 3D tomograms. So 3D tomograms, like I said earlier, they are just 2, 3, 4, 5, or 6 individual tomograms, and then the software patches them together. So in this particular example, we have say 10 centimeters from ground level, 30 centimeters from ground level, 50 centimeters from ground level, and we've done individual tomograms. From that, we can then take the 3 tomograms, put it into the expert software, and the expert software will join the dots in between, and it will give us a column. And in the software, we can rotate the column around, we can turn it, we can twist it, we can zoom in and out and take slices. The display on the Picus 3, you show the bars. Now, these are the important bits for experienced users. The pretty colors, the pretty tomograms are what customers like to see in their reports. That gives them a visual of what they're looking at. While the consultant is on site, they're generally looking at the speeds and the bars, okay? So we can see on this particular example, we will tap in measuring point number 7, and these yellow bars are our time of flight, and the red bars are sonic velocities. And we're looking at these and we're looking for, maybe for example, if we were tapping number 7 and number 2 was down on the ground, we need to verify that number 2 is actually in the wood, the nail's in the wood properly, and the sensor is on the nail. It may have fell off, you may have knocked it off by accident. So that's the important part. Okay, this is the difference between the display. So if you use the Picus in standalone mode, then the display only gives you 3 colors. The 3 colors, brown, fast velocities, green, medium velocities, and pink, slow velocities. It gives you enough information while you're on site. You can see the maximum and minimum velocities of the tree here, but it gives you enough information to say, okay, this tree's got a defect. I need to download this to the laptop in the car, or take further investigation with a resi and just verify why we've got the defect. And then once it's transmitted to the computer using the Q74 software, you'll see this kind of example. Okay, so number 1 here is with the north arrow, number 2, 3, 4, 5, all the way around to measuring point number 12. We have an X and Y axis here of 90 centimeters, so it was a relatively small tree with a couple of defects in there. You can see some short yellow lines. They could indicate cracks, abrupt sound velocity restrictions. And this is the Q74 Expert software photo merge. So we take a photo of the tree, and then we can put the Picus sonic tomogram into the photo, and we can change the transparency depending on how we wish it. We can twist it, we can turn it, we can put it up and down wherever we deem it necessary. And it's just a nice visual, just helps customers visualize where their defect is in the tree. And you can also do it with 3D. Basically, you take the tomogram and you can change the transparency of that in the tree. There we go. So trees are amazing. Any questions, feel free to ask in the Q&A. If you want any further information, pricing, anything like that, then please do give me a shout, Mark at sorbus-intl.co.uk. Okay, John?
Brilliant stuff. Thank you very much, Mark. Really interesting stuff. As Mark said, if you've got any questions, please pop them in the Q&A panel. I'm just going to rearrange my screens here slightly because I'm so technologically minded. We've got a few questions come in. Where shall we go with them all? Let's go to cold hard cash. Question from David at Leeds Council. David's asking, how much is the resi drill and how often is the service? He's also asking, do you take trade for old models?
Yes, we do take trade for old models. So if you have a Resi F, we can do a parts exchange. So contact us with your serial number and we can come back to you with a quotation. The Resi PD 400 for trees, we build a kit for trees and it's in the ballpark of £7,400. So it's a good value for money, shall we say, depending on what you need to do with it.
Well, you definitely would say that, Mark, wouldn't you? It's too good value for money. That's I understand. I understand why you'd say that. Good, thank you. Good question. Thank you, Mark. Right. Okay, let's go to a slightly more critical angle. We can always rely on Anthony for a question like this. Anthony's asking about the fact that you've used the term defect a lot as you've been talking about these issues around the tree. And Anthony's saying that, are we not at the moment all being encouraged to see the other side of the picture? So, you know, what living, sound, structural wood there is. And to call things defect is a bit of a value loaded and sort of pejorative term. Should we be talking about features or characteristics rather than defects?
Of course, yeah, why not? It's just something that's carried over from other presentations that have come from Germany. They tend to use that word over there with some of the presentations that I've seen before. Yes, it's not necessarily a defect. You're right, Anthony.
Yeah, I remember when I was working at Transport for London, we had similar discussions about this, because a defect implies something that needs to be fixed, and then sometimes when you're dealing with a tree and you're talking about a defect, it might not be something that can be fixed or that you want to fix. So it's not always the best term. But yeah, I'm not sure how commonly it's used in other countries, but certainly here, I guess there's other options.
Yeah, totally. Yeah, fully understand that.
Thank you, Anthony. What have we got? We've got a few questions coming in now, crikey. Tom has asked if we can email over the recording to deliver to your students at Myers Co. I'm sure we can do that. I think Steve's put something in the chat about that the recording will be made available to everybody. So anyone who missed a bit or wants to watch it again, don't worry, we can sort that out for you. Where was the question I was going to ask? Good question from Maria here. Maria's asking, is it known how hot it gets in the wood around the drill? And does that heat cause physiological damage to the tree?
There has been some investigation into temperature of the needle shaft, surface temperature, should we say. I believe IML did some investigation into that, and they showed that it was above 60 degrees. So technically, if you're looking at the biosecurity aspect, it's deemed that it could be self-sterilizing. So biosecurity is quite important when you're drilling into the trees. If you're drilling too far, then you can break into that important zone. But also, if you then move to another tree, you need to make sure you're not transferring any pathogens, and you're not infecting any new trees. So temperature is a good one. I can't give you an exact answer to the exact temperature. I guess it depends on the speed of the needle, the force that you're pushing it into the wood, the feed speed, but also the species of wood itself. If you're drilling into tropical wood, then they get so hot that they actually smoke when they come out the end. If you're drilling into a lime tree, then probably not too much temperature.
Brilliant, thank you, Mark. Dan has asked, of the kit you've talked about and described, which, if either, would you use to assess Kretschmeria, and how would you approach this?
So Kretschmeria can be slightly difficult with the pickus because it's so low down within the base of the tree, and if it comes up to a level where you can actually detect it with the pickus, then the pickus will show it as a mottled tomogram, because of the way it affects the actual wood itself. It's like somebody's got a paintbrush and splash paint all over the tomogram. The resi is a good one to use because you can drill below ground. You can drill at 45 degrees into the actual root system. So with that functionality, you should be able to pick it up. And the feed motor itself will show the blue curve on the graph, will show it before the green graph. So you really need to be looking at the feed graph, I would say, with the resi.
Thanks, Mark. While we're going sort of quite specific, let's ask Daniel's question, which is about how many pickus tests have been carried out on ash, particularly ones with ash dieback, and have there been any interesting results?
I would probably struggle to answer that one. It would be more of the consultants that are using it on a day-to-day basis than myself as a supplier. So I'm afraid I can't really give you an answer to that.
Well, that's fine. We've got many knowledgeable people in the audience who are probably on the other end of the thing from you. So if anybody's got any thoughts on that, how effective these are with ash dieback, yeah, please do say in the chat. That was mentioned last week, actually. We were talking about the webinar last week, weren't we, that we did. And Stefan Rust was talking, I think, about ash dieback too. And it's quite difficult to assess with the nature of the disease. It's quite difficult to use this equipment to assess the impact of those diseases.
Yeah, for sure.
Lewis has asked a question here. How do you ensure that you're drilling at the correct height?
Knowledge and experience is the only way that you can tell. So generally what is recommended is that a reference drilling is done, hopefully where there's no decay. So let's say, for example, you drill at breast height. You can use that reference drilling when you go down to if you're looking for a root borne I won't say defect. If you're looking for something coming from the base of the tree, then when you go down below ground, you can refer back to your reference drilling and say that my wood should be looking like this reference, but it's actually not, because all trees are individuals, as you know, and they can all be different. Even at an avenue of 50 lime trees can all come back with slightly different results. So it does come down to knowledge and experience.
Absolutely, always. The tool's only as good as the way in which it's being used, I guess, as well, generally.
Yep.
So, okay, Ari from Indonesia has a Picus 3 and is wondering, can this tool be used to find out the shape and architecture of tree roots?
We can only map the geometry at the level that we're testing at. Picus, Argus Electronic, who manufacture the Picus, originally came up many years ago with a root detector. So it was essentially a big long cable that went out to a root. You find the root and you put the little nail in the root, and then you put the sensors around the tree. When you tap the root, it will come back and tell you whereabouts it's attached to the tree, essentially, and if it's in good condition. I don't think they do that anymore with the Picus 3 because it wasn't that successful. Because of the morphology of the root system, it could be linked to another tree. It could be linked to anywhere. Basket weave of knots of roots underneath, as you know, if you air spade out a root system, they go all over the place. So I would probably say no to that.
Yeah, very reasonable. Oh, Simon Price has just put in the chat. I haven't drilled any with ash dieback. If they're dying back badly, then trunk decay will be a secondary problem. But as Simon says, it would be an interesting study. Yeah, I don't think there's been too much research done on that. That's going back to the ash dieback question. Sorry, folks. I'm jumping around as I normally do. You mentioned earlier on about biosecurity and the risk of moving pathogens from one tree to another. And Nick has asked, what's the latest research regarding breaking through the barrier zones with the drills? Is it likely to allow the fungus to spread?
This argument's been going on for many years, ever since the resi was first invented, I would imagine. Matek did and I have a copy of his paper where he has purposely infected trees by drilling through the barrier zones. And if the tree itself is coping with the decay pathogen, then it just simply shuts down around the barrier. It just moves the barrier around the drill hole. I'm more than welcome to send that to whoever requests it. But yeah, essentially you're only drilling the tree in the first place because there is a problem. And if you don't drill the tree, what can you do? You're going to get the chainsaw out. You need to assess if it's stable or not. So yes, we do need to do the drillings. We don't drill unless we need to drill, and we only drill to the bare minimum.
Thanks, Mark. Benjamin's asking about the kit as well. If using the Resi PD, how many times would you expect to drill to gain a comprehensive impression of a decayed area? And how long does a drill bit last? Benjamin's also asking, can the drill bit be sharpened?
No, it can't be sharpened. It's a hard and steel bit. They are less than £20 each, so it's better just to change them, just to risk. Otherwise, you can eventually it will overstress the needle shaft and they snap. How many times would you drill? Like I said, you drill to a minimum. You only drill until you know that you're happy with the strength of wherever you're testing. If you're drilling softwood trees, then a drill could last up to 200 drillings. If you're drilling hardwood trees, then I would say anywhere between 50, depends on the hardness. If it's tropical wood, then less than 50. If it's what we would call standard hardwood, as in your beech and your ash and your oak, then I would probably say you get a good 100 drillings out of a needle. And they're automatically changed within the drill itself, so it literally takes 5 seconds.
Barbara has asked, do you have to put the species in, or will sort of Sorbus species do? How specific and detailed do you have to get?
Are we talking Picus?
Yes, I think so.
Yeah. Obviously, with the Microdrill, no, we don't put the species. We're just drilling the timber and looking at the resistance. With the Picus system, it's good to have the species because there is a list of standard species, and it knows, or from previous research, the top and the bottom of the speed graphs, if you like. So within the picker software, you select the species, and then from that species, you can say the fastest velocity should be X, Y, Z, and then we can work out bits and pieces. But it's not essential. It's just housekeeping, I guess. The picker self-calibrates to the tree. So the fastest velocity is being brown, and then from there, it works down the scale of color.
Thanks, Mark. Good stuff. Thank you, Barbara. I'm glad that answered your question. Right, Bob has got a question. Hiya, Bob, by the way. Bob says that he finds that putting all the information and the ID number into the PD resi is a bit of a long-winded process. Is there any way you can type it into your phone and just Bluetooth it to the machine?
Not at present. Not as far as I'm aware. I know there is a new app, but I believe it's just for downloading the results. There are utility companies who have developed their own apps. Obviously, that could be quite expensive if you're just a single user, and they download the results from their server to the phone, and the phone talks to the drill and does it that way. The only thing I can say is just when you're entering the tree ID into the ID on the thumb wheel, okay, on the screen, is just abbreviate it. So if you've got a tree tag number, just use that. And then the way I do it is I put the site name, abbreviated site name at the beginning, and then I'll put the tree number, and then from there I'll put the height from ground level, so I know how high I'm drilling, and then the cardinal point or the compass bearing for 360, and do it that way. Basically, because when you move to the next drilling, you're usually at the same height, you're usually on the same tree, you just delete your northeast southwest, or N for north, and then just move around the tree if you need to, and just click W, enter that, and then you've only changed one character. So it's nice and quick and easy that way.
Thanks, Mark. There you go, Bob. There's a shortcut for you. Similar kind of question, bit different, but from Dominic. How easy is it to share the pickers data with a client via email or whatever to back up your recommendations?
Once you've downloaded the data from the Pickers 3, or if you have a Pickers 2, then it will already be on your laptop. So then you can simply click copy, and it copies the image that you can see on your computer screen. You can paste that straight into an email and send a JPEG. Or you can print a PDF and create a Pickers report.
Thank you. Jumping around, there's lots of questions coming in. I think we said we go for about an hour, so we'll keep pushing on for a bit longer.
Yeah,
Padraig has asked, why is height relevant?
With the pickers?
Hasn't been specified, but you answer for whatever you reckon is most appropriate to answer with, and I'm sure Padraig will shout if it's the wrong one.
By saying height is relevant, it's only relevant to where you think that you need to test. So if you have something coming in from the root system, then you need to be as low as practically possible. If you have something coming down from a tear out or some sort of pruning wound, then obviously you need to be at that height. So you need to be at the correct height of where the possible issue is. Otherwise, you'll miss it.
Yeah, makes sense. Thank you. Yeah. Eddie has asked, you've talked about sort of mainly two bits of kit. Eddie's asking, why would you need both pieces of kit?
There's many reasons why you may not need any. There's many reasons why you may need all of them. It solely depends on how much information you need to get from the current tree. It solely depends on your budget and how much work you have for the equipment. So you need to obviously have a business case in the first place to be able to warrant the expenditure. If not, then there's other consultants in the country that can come and do this for you. I would say if you have a Pickus and you get a bad result, then like I said, you need to verify that it is a bad result before you reach for any chainsaws or any work that's going to be a problem to the tree itself or possibly affect the tree, as in cutting it down. Then you need to verify that the result is terrible. And if that is true, how do you do that? The best way, the quickest and easiest way is with a resi. So having the two pieces of equipment from individual manufacturers is a very powerful tool.
Brilliant, thank you. You mentioned there about getting a consultant in who almost sort of knows what they're doing. And Andy's asked a good question. On the basis of the fact that a tool is only as good as its user, do Sorbus have a list of competent or approved PD or PICUS users for our consultants and consultants?
Yeah, we certainly have a list of customers, okay, and those customers dating back from, I think the list goes from 2003, when the first PICUSes were, PICI, whatever you call it, were first starting to be sold into the UK. Now, within the list, there are certain customers that don't use it anymore, have never had any updates on the system since whenever they bought it, and there are other customers that are very good and have it serviced, have it upgraded, have it updated, this, that, and the other. And they've had further training. They've been to some of the master classes that we do or did before COVID, before all that sort of put pay to that. But yes, we do have a list of experienced users that have previously been heard of with good feedback. And if you need any of that information in your local area, we may be able to help you with that.
Great, thanks, Mark. Right, we've only got about a minute left.
Time for the pub. Nearly time for the pub.
It is nearly time for the pub, exactly. all of you out there should be doing far more fun things. Not that this isn't fun, but you know what I mean. Come on.
Here we go.
David has asked, does wood with an altered state always result in acoustic waves traveling slower?
Ooh, that's a question for Stefan Rust, isn't it?
Probably.
That's definitely a scientist answer coming up. I would say yes, tentatively. I probably need to double check that answer.
We can take that as a tentative yes. For any questions that you want to ask that we haven't covered or whatever, you can always email me, john@trees.org.uk, and I can send them on to Mark, and we can send them anywhere else we might need to send them. I'm sure we can get you all the answers you need. But no, good effort. Thank you. Let's go for one more. Tom's asked, is it possible to create a 3D model of the scanned section of the tree using a 3D printer?
Ooh, it's not included in the standard software. So direct from the manufacturer, I don't believe so. But I'm sure there are some clever bodies out there that could maybe do something.
Yeah, that's quite a cool idea though, isn't it? If you get 3D models to show people what's going on inside. I like, Tom, you might be onto something there. You might be onto something.
He's a software developer, is he?
Well, yeah, Tom, get in there and get in there quickly, because there's more than 100 people have heard your idea. So go and patent that very quickly.
Get the patents in quick.
Exactly. Well, look, we said we'd be about an hour. We've been an hour. So I think I'll take this opportunity to sort of close things up and just say, Mark, thank you so much for your presentation.
Welcome.
Really great. You might have seen in the chat, but lots of people very interested in that. So we really appreciate it. Thank you to Sorbus, of course, as well, for all of your support of our show. And thank you to all of you watching. It's lovely to see you as ever. We've got another webinar at 6 o'clock tomorrow. We've got another webinar at 6 o'clock on Sunday. And then, of course, next week, our Wednesday webinar at 6 o'clock too. So there's lots more online content coming up and loads to see and do on Digital Lab shows. So Mark, unless you've got anything you want to sort of finish by saying?
No, that's perfect. Thank you very much for your time. Like I said, if you've got any questions, ask myself or John. We've got our email addresses, or just give me a call. All right.
Fantastic. Thank you very much, Mark. Thank you, everybody. And we will see you hopefully tomorrow evening. Stay safe. Bye-bye.
Thank you. Bye-bye.